So let us revise the module 1 contents, which is useful for your the first test. So first we have to know about what is stress, what is strain, linear stress, linear strain. So whenever a body is subjected to some external force, some internal resistance will develop within the body to withstand the external force. So that internal stress, the internal resistance, whatever is developed within the body, it depends on the nature of the force which is acting externally. If the force is tensile, so tensile stress will develop. If the force is compressive, compressive stress will develop. It is expressed as the resistance force developed within the body per unit area. So that means the unit of stress is Newton per mm square or MPa, megapascal. Newton per meter square is called as Pascal. So you have studied that in FM, fluid mechanics, that fluid pressure is expressed in pascals and also in kilopascals. Whereas stresses are expressed in megapascal. That is the difference. Kilopascal means 10 power 3 Pascal. Megapascal means 10 power 6 Pascal. So here megapascal can also be written as Newton per mm square. So stresses are expressed in Newton per mm square. Where area is in millimeter square and the resistance is in newtons. So that force is nothing but your resistance force. Okay. Now you have one property in every material called elasticity. So whenever a material is subjected to some force, it deforms. The tendency of the material of the body is to deform, maybe depending on the type of the force. If the force is tensile force, the material elongates. See, the body will elongate like this. If the force is compressive, it contracts. So, as a simple example, if you take a bar of rectangular section, some or circular section, something like this, if it is subjected to tensile force, tensile stresses will develop within the body, and the length of the body will increase, and the diameter or lateral dimension, maybe width or depth, so it will reduce. So, if elongation is there in one direction, naturally in the other two directions, you will be having contraction. So once you remove the force, if it can regain its initial shape and size, then we say that the material is in elastic condition. So best example is rubber. So when you stretch rubber, so its length increases. But when you remove that stretching, when you stop that stretching, it comes back to its initial shape and size. So that is the best example for elastic. But all the materials they have got elastic property up to certain limit. Then, if it won't regain its initial shape and size, then we say that the material has gone to plastic state. So plastic state means permanent deformation takes place within the body. Whereas elastic state means it is only under temporary deformation, and if you remove that force, it will regain its initial shape and size. So that is the property of elasticity. Plasticity means it won't come back to its initial shape and size even after removing the force. Okay. So as I already told, we can have two types of normal stresses. Normal stress means the stress will act perpendicular to the plane of the area. So tensile stress and compressive stress, they are called as the normal stresses because they act perpendicular to the plane. For example, so this P2 is the force which is acting on the cross section of this ball. So maybe circular or rectangular. It acts perpendicular to that. That is why it is called as direct stress or normal stress. So two types of stresses, direct stress or normal stress are tensile and compressive. And due to tensile stress, you know that you have elongation. Due to compressive stress, you have contraction along the linear direction. Since the stresses are represented along the linear direction, we call it as linear stress also. So there is one more stress called shear stress or tangent shear stress, which acts parallel to the plane of the area. That is perpendicular to this tensile or compressive, we have one more stress called shear stress. Okay, that is also called as tangent shear stress. It will act like this. Suppose if you take the top area here, this area, shear stress will always act tangential to that area. So once again, that force divided by the area of that plane surface gives the shear stress. Now coming to the strain. So strain is defined as the ratio of change in that is a ratio of the change that is an amount of deformation to the original dimension. Change in dimension to original dimension. Suppose if you are measuring the strain along the length, it is called as linear or longitudinal strain, where it is denoted as delta L by L. So delta L is the change in length, L is the initial length. Or if you are measuring the strain along the lateral means perpendicular to the linear, it is lateral. Along the length, it is linear. Perpendicular to it, it is lateral. So lateral or transverse. So as I already told, if it is subjected to tensile force, tensile strain will be there along the linear direction, whereas compressive strain will be there along the lateral direction. So because the dimensions in the lateral directions, they reduce. So maybe diameter or width or thickness. So this ratio of change in dimension to initial dimension is known as strain. Now there is one important law called Hooke's law. Within elastic limits, that means when the material is in the elastic limit, stress is directly proportional to strain. Linear stress is directly proportional to linear strain. That means if you plot a graph of stress along x-axis to strain along y-axis, stress along y-axis to strain along x-axis, so you'll be getting a curve like this. So initially it will be straight line. So up to this it is elastic state. Then it will take a curve shape. That means the material has gone to plastic state. So note that stress is expressed in Newton per mm square. Strain does not have any unit because it is the change in dimension to initial dimension. So you don't have any unit for strain, just a number. So stress is directly proportional to strain. It is written like this: sigma directly proportional to epsilon. Sigma is the stress, epsilon is the strain. When you replace this variation sign by equality sign, so stress is equal to Young's modulus into strain. So you will introduce a constant called Young's modulus E, or it is also called as modulus of elasticity. So whose unit is once again Newton per mm square. For example, for steel, the value is 2 into 10 power 5 MPa or Newton per mm square, or 200 GPa. So please note that 1 GPa is 1000 MPa or Newton per mm square. So this value of Young's modulus vary from material to material. Now some assumptions we are making in simple stress theory. Material is homogeneous and isotropic. That means the physical property of the material is same in all the three directions, x, y, z direction. That is homogeneous. Isotropic means the elastic properties, Young's modulus, Poisson's ratio, all those things, they are constant in all the three directions. That is called as isotropic. Deformations are very small and are within the elastic limits. That means we are applying simple stress theory only within the elastic limits, that is within Hooke's law. The material is assumed to be in elastic state. So stresses developed are within elastic limits. Material obeys Hooke's law. Plane sections remain plane even after the application of external forces. So please note that force is an external agent, whereas stress is an internal factor which develops to resist the external force. Now one simple derivation we have done: deformation of a uniform bar. Uniform bar means cross section remains same. It is also called as prismatic bar. Throughout the cross section remains same. So L is the length of the bar. Let us assume that P is the tensile force acting on that bar. So due to the tensile force, the bar elongates. The initial length is L. Final length I will take it as L plus delta L. That means delta L is the increase in length. So according to the definition, stress is internal resistance divided by area. When force is P, resistance also will be P. So P by A. Area is the area of the cross-sectional area of the bar. Strain is delta L by L according to definition. Now according to the Hooke's law, sigma is equal to E into epsilon, or E is equal to sigma divided by epsilon. So sigma is P by A divided by epsilon delta by L. If you cross multiply and rearrange the terms, you will get very simple formula PL by AE. So delta L is equal to PL by AE is the formula used to find the elongation or contraction of a prismatic bar or uniform bar of same cross section throughout. So please note the units. P is in newtons. P should be in newtons. L will be in millimeters. A will be in millimeter square. E will be in Newton per mm square. So you are going to get delta L in millimeters. Okay. So when the force P is tensile, delta L is elongation. When the force P is compressive, it is contraction. So depending on the cross sectional area, we have to take the depending on the shape of the cross section, we have to use this respective formula to find the area. So for circular bars, A is equal to pi d square by 4. For rectangular bars, A is equal to B into D. So that is depth into depth. So this is for uniform bar. Then one more derivation we have done for deformation of a circular tapering bar. So circular tapering bar means the diameter of the bar varies gradually like this. Either it may increase or decrease. So D1 and D2, they are the diameters of the two ends. L is the length of the bar. So for derivation purpose, we have to take a elementary length dx with diameter d suffix x at a distance x from the first end. And this is the derivation we have done. So we have considered the small length and we have found out the delta L for the small length, and then we are going to integrate that between the limits 0 to L. That's what the derivation. We have to go through that. So finally, you will be getting the, after substituting and integration, after integrating the terms, we will be getting the formula like this. If they ask the derivation, you have to do this. Problem if they give, so this is the formula we have to use for changing length in the case of tapering circular bar. D1, D2, they are the diameters. L is the length of the bar. P is the force acting on the bar. E is Young's modulus. So P should be in Newton. L will be in millimeters. D1, D2 in millimeters. Okay. E will be in Newton per mm square. If force P is tensile, there will be elongation of the bar. If force P is compressive, there will be contraction of the bar. So same formula holds true. Only thing is, depending on the nature of the force, you will be having tensile or compressive. Normally, what we take is delta L is positive if it is a tensile force because the length increases, and delta L is taken as negative if it is a compressive force because length decreases. Similarly, you have another derivation, deformation of a tapering rectangular rod of uniform thickness. So you have a rectangular bar like this, thickness is same. The thickness is T from here to here, but the width varies. Okay, width varies from B1 to B2. Thickness is same. So the area here is B1 into T, area here is B2 into T. Okay. Now, based on the similar principles, first principles which we did for circular tapering rod, if you do the derivation, considering a small elemental length here of width b suffix x at a distance x from the first end, and doing the same integration type, you will be getting the formula like this. So this formula you should remember, PL by TE into B1 minus B2 into log to the base E B1 by B2. Where B1, B2 are the widths at the two ends, L is the length of the bar, P is the tensile force or compressive force, E Young's modulus, T thickness, B1 and B2 they are the widths. So B1, B2, T they will be in millimeters, L also will be in millimeters, P will be in newtons, P1, okay. So then you will be getting delta L or DL, whatever it is, you are going to have in, we are going to get it in millimeters, okay. Then we discussed about bars with varying cross sections. So yeah, may vary. So this is a single entity, but it has got three portions. First portion length is L1, second one L2, third one is L3. May be made of same material or different material. So P is the force acting throughout. On all the three portions, tensile force acting is P only. Tensile force acting is P only. That means it will elongate. D1 is the diameter, D2 is the diameter. Otherwise, they may give thickness and width also. If they give thickness and width, then it is rectangular cross section. So you have to take the area as width into thickness. Since it is circular, you have to take the area as pi d square by 4. So area of this will be pi d1 square by 4. Area of this will be pi d2 square by 4. area of this will be pi d3 square by 4. Okay. Now in such types of problems, when force is same on all the portions, so we have to add the deformation of each portion separately. So for example, like this. Let us take delta N1, delta N2, delta N3. They are the deformations in the three portions. Then your total deformation will be the sum of all the three. So we know the formula for finding deformation of a single bar, uniform bar, PL by AE. That is the formula. Here, since the same force is acting on all the three portions, so P remains same, but lengths are different, areas will be different. If it is of same material, E value will be constant. So this is how we have to write. But in some cases, they may give different forces also that we will see. Now here also, here the difference is here it's uniform, but it is tapering here. Second portion is tapering. Third portion is uniform. So you have to see to the nature of the cross section of the bar. So and you have to use the respective formula. The first formula is uniform portion. So PL by AE. Third one is uniform PL by AE. But second one is tapering, circular tapering. Therefore, we have to take 4 PL by pi E d1 dt. So that formula. So when the here of course the force is taken as compressive here, just for understanding. So compressive means you same formula is valid, but only thing is contraction will be there. Contraction will be there. So be careful about the units when you are substituting in the formula. P you have to take in newtons, length millimeters, area millimeter square, E value Newton per mm square. And some problems we have done. See here. See here. This is 100 mm, 150 mm diameter. Length is 200 mm. This is 100 mm diameter. Length is 150 mm. Here 200 mm diameter, length is 250 mm, subjected to same force 100 kilonewton. All the three portions are subjected to same force 100 kilonewton. Calculate the total deformation and the stress in each bar, deformation in each bar and the total deformation. Also find the stresses in each bar. Simple problem. So E value is given 2 into 10 power 5 MPa, that is steel. So what we have to do, each bar we have to take separately and we have to find the deformations. So delta L1, first bar PL by AE, PL1 by A1 E, because P and E are constants here. Same force is acting on all the three bars, so P value is same. Young's modulus is same material is used. So only L1 and A1, L2, A2, L3, A3. So those things we have to find out. Since it is circular cross section, area is pi d square by 4. The corresponding diameters we have to take, Young's modulus is same. Corresponding lengths we have to take. So the value of delta L1, delta L2, delta L3 you will be getting in millimeters. Since it is tensile force, all the portions will be subjected to elongation only. Then we have to add all the three deformations to get delta L. And the stresses if you want to find, stress is given by force divided by resistance divided by area. Resistance is the force itself. P by A1 gives the value of sigma 1. So sigma 1 is the stress in the first portion. Sigma 2 in the second portion, sigma 3 in the third portion. So these values will be Newton per mm square. And one more thing I have told in this, suppose if they ask you to find the strain in each bar. So in first portion, strain is given by delta L1 by L1. Okay, epsilon 1. That has not been done here. But if they ask you to find the strains are represented as epsilon 1, epsilon 2, epsilon 3. Epsilon 1 is delta L1 by L1. Epsilon 2 is delta L2 by L2. Epsilon 3 is delta L3 by L3. Okay, you know the values of delta L1, delta L2, delta L3. L1, L2, L3 also you know. Just take the ratio, you are going to get the strains in the three bars. Otherwise, you can do in another way. After finding stress also, you can find out strain. According to Hooke's law, stress is equal to, the stress is directly proportional to strain. That means sigma 1 is directly proportional to epsilon 1, or you can write sigma 1 is equal to E into epsilon 1. So therefore, epsilon 1 is equal to sigma 1 divided by E. So if you substitute for sigma 1 and E, then also you will get same value. So epsilon 1 is equal to sigma 1 divided by E. Epsilon 2 will be sigma 2 divided by E. Epsilon 3 will be sigma 3 divided by E. So like that we can find like this or like that. So you will get the same answer. So strain can be found out in two ways. One formula is strain is equal to epsilon is equal to delta L by L. The other formula is epsilon is equal to sigma divided by E. That's what has been explained. Now, in the next problem, of course, this is a bookwork problem. We can just go through that derivation type. So, if the diameter varies from D plus A to D minus A, what is the percentage error in computing the change in length? That is the numeric. That is a bookwork. You can just see that. Now, I want to explain this problem. Here, the different forces are given here. So, all the three, even though it has got three portions here also, they are not subjected to same force here. You can see a 10 kilonewton tensile is acting here, 20 kilonewton is given here. See the arrows, arrows are very important. 10 kilonewton is acting here, 20 is acting here. So in such a problem, here also we have to find out the uh, total along deformation of the bar and also stresses and strains in the segments. Segment means those portions. So E value 2 into 10 power 5. Once again, it is steel. See here, areas are given, lengths are given. 500 mm square, 400 mm square, 600 mm square areas. Lengths are 180 mm. Then second one is what is that value? Second one is 220. Yeah, 220 mm. Third one is 200 mm. Okay, L1, L2, L3, A1, A2, A3 are given. But even such problem is given, forces are different here. So all the three portion segments are not subjected to same force. So one by one we have to find out. I have explained that how to find that. All of you observe. So first you take the first portion. First portion, whatever force is acting on that to the left side, you write down that 10 kilonewton. I am separating all these three. So you write down all the three separately. First portion is subjected to 10 kilonewton tensile. Only left side you take. Now to have the equilibrium of this, we have to take another force 10 kilonewton acting towards right at the other end. Then the bar is in equilibrium. Okay. So opposite direction we have to take like this. Next, take the last portion. Take the last portion. In the last portion, rightmost 20 kilonewton. So it is acting like this. Okay, 20 kilonewton is acting like this, and opposite direction it will act. To keep this in equilibrium, 20 kilonewton in opposite direction it will act like this. Okay, we have to introduce this. Now write down the middle one. In the middle one, already he has given 20 kilonewton towards left, 10 kilonewton towards right. So those two you write down. Now at this junction, I have introduced a 10 kilonewton in this direction to keep this in equilibrium. So what I have to do to balance this 10 kilonewton, I have to take another 10 kilonewton in the opposite direction at the junction. So this 10 kilonewton is to balance this one. So to balance this one, we have written this. To balance this one, we have to write this. Similarly, this side, 20 kilonewton is acting like this. Another 20 kilonewton is acting. To balance this 20 kilonewton, I have to introduce another 20 kilonewton like this. To balance this 20 kilonewton at this junction, I have to take 20 kilonewton in the opposite direction like this. Okay. Now come to the second middle portion. What is the total force acting here? 20 plus 10, 30. Here also 20 plus 10, 30. So they are tensile. They are acting in opposite direction. Therefore, this portion is also in equilibrium. So this is how we have to do. The first and last we have to take. Then we have to decide the force acting on the middle one. Now, one by one we will take delta L1 for this, delta L2 for this, delta L3 for this. So delta L1 is P1 L1 by A1 into E. So P1 is here 10 kilonewton. Okay, L1 is 180 mm. A1 is 500 millimeter square. E value 2 into 10 power 5. So this kilonewton should be converted to Newton. Be careful here, because stresses we are expressing in Newton per mm square, Young's modulus in Newton per mm square. So kilonewton should be converted to Newton, and meter, centimeter should be converted to millimeter. Next here, so substitute that, you will get delta L1. Of course, it is positive here because it is tensile force. 10 kilonewton is tensile force, delta L1 is positive, elongation. Next, delta L2 is the deformation in the second portion. 30 kilonewton is the force here. So 30 into 10 cube, length is 220 mm, divided by area is 400 into E value 2 into 10 power 5. If you substitute that and simplify, you will get 0.0825. Okay, this is also positive because it is also tensile force. Next, delta L3, P3 L3 by A3. Here 20 kilonewton is the force acting here. So 20 into 10 cube, length is 200 mm, area is 600 mm square, E value 2 into 10 power 5. You will simplify that this. So this is also positive because this is also tensile. That means all the three segments, they are subjected to elongation only, because the forces acting on all the three segments, you can see that they are all tensile forces. The elongation takes place in all the three. So if you want total deformation, just add them. All are positive here. Suppose in any of the segments, if you get the compressive force by arranging this, let us say instead of this 20 given like this, if they give 20 compression, then in this portion you will be having contraction. That is delta L3 will be negative. Suppose if 20 kilonewton is compressive, then delta L3 becomes negative. Okay, that is the mean. So you have to take minus. Then when you are adding, you have to take the sum algebraically. So in this case, all the three are positive. Therefore, you have to add. Suppose if one of them is negative, then you have to subtract. Suppose if this delta L3 is negative, then this is plus this minus this. Like that you have to take. That is the total deformation. In this case, since all are positive, we have to just add all of them. That is the value. Now he has asked stresses also. He has asked all the three portions in this problem. They are subjected to tensile stress only. Just divide by the resistance force by the cross sectional area. You are going to get the corresponding stresses. So all are tensile stresses. P1 by A1 gives sigma 1. P2 by A2. So P2 is here 30 kilonewton. P1 is 10 kilonewton. P3 is 20 kilonewton. So convert that to Newton, divide by the corresponding area. Here area is directly given. Sometimes they will give diameter, then pi d square by 4 you have to use. If they give rectangular bar, width and thickness they will give. So that you have to multiply. Width into thickness gives the area. Here directly he has given the area. So these are the stresses you are going to get. All are tensile stresses. All are tensile stresses. Suppose if they ask in the same problem, strains, then as I already told in the earlier problem, epsilon 1, epsilon 2, epsilon 3. So epsilon 1 will be sigma 1 divided by E, epsilon 2 will be sigma 2 divided by E, epsilon 3 will be sigma 3 divided by E. Otherwise, you can take epsilon 1 as delta L1 by L1, epsilon 2 is delta L2 by L2, epsilon 3 is delta L3 by L3. So any formula you can use, either that or this. That is about when they give various different forces acting on the different segments. In this case, in this problem, P is unknown here. He has given 300, 250, 100, but P has not given. Even if he has not given, he can calculate that by equilibrium. So equilibrium means whatever forces are acting towards right, it should be equal to sum of the forces acting towards left. That's all. So here 300 plus P. See here 300 plus P. They are acting towards right. It should be equal to 250 plus 100. That is 350. Therefore P becomes 50. Very simple calculation. So consider the equilibrium of the entire bar of varying cross section. Force sum, you equate the sum of the forces acting towards right to the sum of the forces acting towards left. Find out the unknown force. Then remaining thing, once you get the value of P, then you can substitute that value, and as usual, like the earlier problem, you just take the first portion and last portion, write down the forces, then balance the middle one. Okay, so 100 kilonewton is there here. So to balance that, you have to take 100 kilonewton towards right, and here also 50 kilonewton is acting towards right. To balance that, we have to take 50 kilonewton towards left. Okay, now take the middle one. So 300 is already given here towards, so take that 300, and 250 is given like this, so take towards that. So that means these two are compressive. Then to balance this 100 kilonewton, I have to introduce 100 kilonewton in the opposite direction. To balance this 50 kilonewton, I have to introduce 50 kilonewton in this direction. So then the total will be now 300 like this, 100 like this means it becomes 200. 200 like this. Here also it is 250 like this. 50 like this means we have to take the difference. Effective will be 200 in this direction. So what we can say finally, first portion is subjected to 100 kilonewton tensile. So delta L1 will be positive, elongation. Third one also tensile, 50 kilonewton. So delta L3 is also positive, elongation. But when you come to second one, it is compression, compression of 200 kilonewton. So the effect of this 300 minus 100 we have to take because they are acting in opposite direction. And net final effect is compression. So 200 compression means delta L2 will be negative, compressive. Okay, so contraction takes place. So if you calculate, see here, minus I have written minus because it is compression. So it is contraction, elongation, elongation. When you add all these three, so this minus this plus this, you will get total finally delta LS minus 0.036 mm. That means finally total deformation of the bar, the entire bar has contracted. Then you can find out the stresses using the same formula, P1 by A1, P2 by A2, P3 by A3. So first and last tensile stresses, the middle one, sigma 2 is compressive stress. Okay, so I have not written here, you can write the tensile stress, compressive stress, tensile stress. Then if they ask you to find the strains, same formula, epsilon is equal to sigma by E. So epsilon 1 is equal to sigma 1 by E. Epsilon 2 will be sigma 2 by E. Epsilon 3 will be sigma 3 by E. Or you can use another formula. Epsilon 1 is delta L1 by L1. Epsilon 2 is delta L2 by L2. Epsilon 3 is delta L3 by L3. So it has no units. Strain has no units. So that is another problem. In this problem, it is restrained at both the ends. That means there is, instead of force, they develop a reaction here. So the elongation, total elongation is 0 here. Please note that when they give a problem like this, there is no elongation here or contraction. Neither elongation nor contraction because the ends are fixed here. When fixity is there, then it cannot move. So in the other problems, it is free. There is no support there. So that is why it can elongate or contract. But here, it cannot elongate, it cannot contract. So 275 mm length, 150 mm length, 325 mm length, 30 kilonewton, 60 kilonewton. So in this problem, find the reactions. So we have to find the reactions here. A, B, C, D. RA is the reaction here. RD is the reaction here. Okay. So what here, of course, here it is a uniform diameter. 25 mm is the diameter. Area is same. Now, since the ends are fixed, total elongation of the bar delta L is equal to 0. That is very important thing here. This is very important. Since the ends are fixed, even if one end is not fixed, then it can elongate or contract at that end. So elongation contraction takes place at the free end. So since here it is fixed, so delta L will be 0. Final delta L will be 0. Now, suppose if I take this as P, this reaction as RA as P, if you apply the equilibrium equation, P is acting towards right. So P plus 30 should be equal to 60 plus RD. So then your RD will be P minus 30. That's what. So now take the portion separately as usual. First and last you write. In the first one, P is acting. So this RA I have taken it as P. Last one, P minus 30 is acting like this. So this is also compression. This is also compression. Middle one will be 30 is already given here, compressive. 60 is also given in this direction. Now to balance this P, we have to take another P in the opposite direction here. To balance this P minus 30, I have to take another P minus 30 in the opposite direction. Now let us see what happens to this. This becomes 30 plus P because both are acting in the same direction. This becomes 60 plus P minus 30. That means there is also 30 plus P. That means all the three they are subjected to compression here. First one is subjected to compression P. Second one subjected to compression 30 plus P. Third one subjected to compression P minus 30. Now we know that the total deformation is 0 because it is fixed at the two ends. So if you use that concept, so delta L1 plus delta L2 plus delta L3 should be 0. Use the formula PL by AE formula. So P is the force in the first one, P plus 30 is the force in the second one, P P minus 30 is the force in the third one. So P is the unknown here. So L value you know, A value you know, A is constant, E is constant here. So just substitute there and simplify for P. So P you are getting 7,000. 7,000 means it is in Newton. Convert that into kilonewton, 7 kilonewton. So you are getting P as 7 kilonewton. Okay. Then once P is 7 kilonewton, your RA is nothing but 7 kilonewton now. RA is nothing but P. Reaction at A is P here. See, that's what. Then RD will be P minus 30. So P minus 30 means 7 minus 30, which is minus 23. So the meaning of that is, we have assumed initially RD like this, RD in this direction. We have assumed it. We don't know. Initially, we have to assume towards the support I have assumed. But after calculating, you are getting negative sign, minus 23. So RD is minus 23 kilonewton means it is acting in the opposite direction. Like that we have to take. That means RD is acting in the opposite direction. So that is what they are the reactions. So I have shown here. I have arrow. Then suppose if they ask you to find the stresses and strains or the deformations in each bar. So deformation in the first bar is PL by AE only. So here see, this is the deformation in the first bar, delta L1. So this is a constant, 275 divided by this whatever is there is a constant. That constant is this value multiplied by P. Once you get the value of P, so P is taken as 7,000 because it is in kilonewton here, substitute in Newton. So 7,000 into this gives is the value of delta L1. Similarly, delta L2 is this one. Substitute for P as 7,000. So, no, actually 7 plus 37. 7 plus 30, it is 37. So, 37 into 10 power 3. Please note. So, P is 7. 7 plus 30 means 37 in kilonewton. In kilonewton, it is 37. So, 37 into 10 power 3 in newtons. So, that if you substitute in this, 37,000 if you substitute here in this place, you will get delta L2. Here 7 minus 23 means it is 23 only, minus 23. Minus 23 into 10 power 3. So if you substitute that, you will get this value. So that means here, the first one is, what happens here, the last one is acting like this, that means it becomes a tensile. So see here, initially we have assumed RD like this. Initially we have assumed like this, but RD we got negative. That means it acts in the opposite direction, means it becomes tensile. Tensile for this. See, this becomes tensile. RD will be in the other direction. It becomes tensile. Tensile means the elongation. Elongation takes place. So your delta L3 is positive. See here. So these two are negative because compression. This is tensile, so positive. Then stresses, strains you can find as usual. Stress is given by P1 divided by P1 is 7 kilonewton. So 7 into 10 power 3 divided by A1. So sigma 2 is P2 by A. P2 is 37 kilonewton. Sigma 3 is 23. So only thing is first two are compressive stresses. Third one is tensile stress. Then if you want strain, so delta L1 divided by L1 is the strain. So there is compressive strain in the first portion. Delta L2 by L2 is the compressive strain in the second portion. Delta L3 by L3 is the tensile strain in the third portion. Okay. Otherwise, you can find out epsilon 1 is equal to sigma 1 by E. Epsilon 2 is equal to sigma 2 by E. Epsilon 3 is equal to sigma 3 by E. Like that also you can find. So that is another type. Now, next problem. So here, hanging bar. In the case of hanging bar, same procedure is used. We have to, when you want the total deformation, it is the deformation of this portion plus deformation of this portion. So instead of giving horizontally, it has been taken vertically, that's all. So you can study this problem yourself, similar to the last problem. So you have to take the two portions separately and you have to do. And here, this is a bar, this is a portion in which up to this it is solid, then there is a hollow portion. A hole is drilled here. And he has given that 25 kilonewton is the force, tensile force acting over the entire system. But here, he has given the length 600, then this is 400 mm. And the diameter is 30 mm here, 30 mm. Here this drill hole diameter is 10 mm. So when you are taking the area of this portion, it is pi d square by 4. So pi into 30 square by 4. When you are taking the area of this portion, it is pi by 4 into d square minus d square. That is 30 square minus 10 square. That's all the difference. The remaining things are same. So that area of that drill portion we have to subtract from the total area. So like this, the problems have been done. Here also, similar type of problem. Only thing is the compressive stress. Instead of giving horizontal, it has been given vertically. Aluminium, steel, two different materials are there. Areas are different. Young's modulus is different. Just we have to add the deformation in this and plus deformation in this. Both are compressive here because P is a compressive force here. So P is unknown here. Other things they have given. If the total contraction is 0.25 mm, find the value of P. So simple. The only thing is either they may give force unknown or stress unknown or strain unknown like that, depending on the problem. So due to self weight, so sometimes if a bar is hanging like this, fixed at the top, then if you consider the weight of that bar, due to weight of the bar also, you will be having deformation. That derivation I had explained. So this is the deformation due to self weight. Gamma L square by 2E, where gamma is the density of the material. Okay, gamma normally it is expressed in Newton per millimeter cube. Please note that unit of gamma is Newton per millimeter cube. L will be in millimeters, E will be in Newton per mm square. So this is a simple derivation by taking elemental strip, by taking that elemental strip and applying the formula of PL by AE. So this is the elemental strip. So you can calculate the deformation due to self weight of a cylindrical bar. This is cylindrical bar. That means the area remains same. Similarly, you can have for conical bar. For a conical bar, this is the formula. They may give problem. Just gamma value they will give. L will be given. E will be known. So just simplify that. So you can see that elongation of a conical bar due to its self weight is 1/3 of the due to its 1/3 of the elongation of a uniform bar. So because it is gamma L square by 6E here for conical bar, whereas for cylindrical bar it is gamma L square by 2E. So 2E is there, that is 6E is there. So it is 3 times more. Or this is 1/3 of that. So these two bookworks you can just derivation is similar, and this also you can go through. Then all these types I have covered. Okay, so these are additional examples which has been done. So same problems you can work it out so that so here see one uniform bar is there, then tapering bar is there. So we have to apply PL by AE formula for this. We have to apply 4PL by pi E D1 D2 for this. That's what see. So total elongation is the sum of these two. So all these types of problems I have covered. Then the next thing is we have to take a tensile test. When a mild steel specimen is subjected to tension test, tension test means the specimen is subjected to tensile force, gradual tensile force, and deformation is measured using extensometer. This instrument called extensometer or strain gauge. Either by using strain gauge or extensometer, deformation of the rod is measured, and stress versus strain graph is plotted. So stress is whatever load is applied divided by the area, initial area. Initial area diameter you will be knowing. Pi d square by 4 is the initial area. Load divided by initial area gives the stress value. Strain value is given by change in length divided by initial length. So initial length are called, it's also called as gauge length. Initial length is also called as gauge length. So when it is subjected to tensile test, when the load increases, stress also will increase because P by A is the formula, you know. So initially, if you plot a graph of stress of y-axis along y-axis, strain along x-axis, initially it will be a straight line. So the straight line portion represents the Hooke's law, elastic range. Then it will increase, then decrease, then once again increase, and then will decrease. So it's a curve portion. Here there are different points. A is called as the proportionality limit, B is called as the elastic limit, C is the upper yield point, D is the lower yield point, E is the ultimate point, F is the breaking point. So this is a typical stress strain curve. got for mild steel when it is subjected to tension test in laboratory. So actually in the lab it is there, this experiment is there. So from the graph we can always find out the E value, Young's modulus value. The purpose of finding the conducting tension test is finding Young's modulus value. So in the straight line portion, that is in the elastic portion, we have to take the slope of that line. So your ordinate is stress, abscissa will be strain. So you can take 2 points, any 2 points, sigma to sigma 1, they are the stresses at those 2 points. Epsilon to epsilon 1, they are the strains at those 2 points. If you take the slope, that is tan theta, that gives the Young's modulus. Then you can always compute the percentage increase in length, percentage decrease in area. So when it is subjected to tension test, length will increase, area will reduce. That's what. So area of the specimen will reduce. So you have to note down the initial diameter, final diameter at failure. So if you take final diameter at failure as D1, then pi D1 square by 4 is the final cross-sectional area. Final length is L1, let us say. So naturally N1 is greater than L. Final length is greater than initial length. And final area will be less than initial area. So therefore percentage increase in length is given by this formula. L1 is greater than L, so a difference you have to take. L1 minus L divided by L into 100 percentage. Decrease in area is given by A minus A1 divided by A, because initial area is more, final area is less. So A minus A1 divided by into 100 in percentage. So they are the things they may ask, and they may ask you to find ultimate stress, breaking stress, all those things. So naturally it is given by the corresponding load divided by the area. So ultimate stress is nothing but ultimate load divided by initial cross-sectional area. Breaking stress is nothing but or failure stress is nothing but failure load divided by the initial area. So there are two stresses that are defined, nominal and true stress. Nominal stress means it is load divided by initial cross-sectional area or original cross-sectional area, whereas true stress is the load divided by final cross-sectional area. So true stress is always greater than nominal stress because A1 is less than A. So there is one thing called factor of safety, which is nothing but the ratio of ultimate stress to safe stress, where safe stress is nothing but the maximum stress for which any member has to be designed. So if the stress in that material exceeds that safe stress, the material will fail. It will break. That is the meaning. And one or two problems I have done on this. You have to go through that. So sometimes you may have to draw a graph on a graph sheet, and I of course I will give that later on a simple graph sheet. In the laboratory, you are going to do that stress versus strain. So in the data, they will give load and deformation. That's all. Load and deformation they will give. That is P value and delta L value they will give. So P divided by A gives stress. Delta L divided by L gives strain. So stress versus strain graph is drawn. Then from that graph, you are supposed to find out Young's modulus, percentage increase in area, percentage decrease in percentage decrease in area, percentage increase in length, all those things. Okay. And some properties I have defined for the materials. You can go through that. Compound bars is another important thing. Whenever you have, up to this we have covered only simple bars. Only one material was there. Compound bar means whenever more than one material, two or more materials of same length or different length are subjected to tension or compression, that is axial force. Why it is called as axial force? Because they are acting along the axis of the member. So tensile and compressive forces, they are also called as axial forces because they will be acting along the axis of the member. In the case of composite bars, we have to use two important conditions. One is called as the equilibrium condition. According to the equilibrium condition, whatever total force is acting on the system, it is shared by the two bars, two or three bars, whatever it is. So here I have taken steel and brass. So this case, okay. So you can write total force P is shared by these two. That is one condition, and we know that force is equal to stress into area. So PS is sigma S into AS. Sigma S is the stress in steel. AS is the steel area. Sigma B is the stress in brass. AB is the area of brass. Okay. So if you use this formula, this is equilibrium condition. Strain compatibility condition, second one. So say according to strain compatibility condition, your change in dimension in all the bars will be same. That is delta LS is equal to delta LB. So delta LS is found out using this formula. PSLS by ASES is equal to PBLB by ABEB. So PL by A is the general formula we are using for steel. So whatever load is shared by steel multiplied by the length of steel divided by area of steel into Young's modulus of steel. So by using these two, so here this PS by AS can be written as sigma S. Okay, PB by AB can be written as sigma B. So you'll be getting another equation like this. See, suppose if the lengths are same, then LS and LB can cancel out. So this is how you will get. If they are of same length, if they are of different lengths, then you have to use this. Anyway, all the lengths you will be knowing. So in this, when you are using these two conditions, one equilibrium, another one plane compatibility condition, so you can find out the stresses in the bars. Sigma S and sigma B can be found out. So you will be knowing the total load. P you will be knowing, AS, AB will be given, and ES, EB will be given. Okay, and LS, LB also you will be knowing. So unknowns will be sigma S and sigma B. So they are the two unknowns. From two equations, you can solve those two unknowns. And later on, you can find out the other things, change in length, all those things you can find out. Once the stress values are known in the two bars, then you can always find out the deformations. So by substituting in any of these. Once stress values are known, you can find out the deformations. So problems are done on this. See here. See just one problem I'll explain. Yeah, see this problem. Here you have a copper tube and steel rod. A compound bar consists of a circular rod of steel of diameter 20 mm, rigidly filled into a copper tube of inner diameter 20 mm and thickness 5 mm. So thickness of the copper tube is 5 mm. This is the cross section. 20 mm is inner diameter, thickness is 5 mm, and steel rod has got a diameter of 20 mm. So steel is within copper. If the bar is subjected to a tensile force of 100 kilonewton, so this is subjected to that force I have not shown here. We can take the arrow away from the bar, tensile P, 100 kilonewton. Find the stresses in the materials, loads shared by the materials. So Young's modulus of steel and copper they are given here. So as I already told, find out the first to find out the areas. Total force here is 100 kilonewton. So that 100 kilonewton is shared between steel and copper, not equally. Okay, it is not shared equally. We have to find out the ratio of the forces here. P is 100 kilonewton. AS and AC you have to calculate. Area of steel. Steel is a solid circular section here. It's a rod, pi d square by 4. Whereas the copper is a hollow circular section. So pi by 4 into outer diameter square minus inner diameter square. That is the area. So those areas are found out. Now use the first condition is equilibrium condition. This is the equilibrium condition. So we have to find sigma S and sigma C. Stress in steel and stress in copper we have to find out. So you know the areas. So you know force P. P is equal to sigma S AS plus sigma C AC. We express one stress in terms of the other. Okay. So express sigma S in terms of sigma C. That is one condition. Next, second condition is strain compatibility condition. According to that, the deformations in both the bars they are equal. So delta LS is equal to delta LC. So here LS is equal to LC. In this case, both the lengths are same. He has given same length. If they give different length, you have to take different, substitute there. But here it is given same. So PL by AE, if you use that, you are going to get this. Using this, you will get another relationship between sigma S and sigma C. So sigma S is equal to sigma C 1.667 times sigma C. You have got this. Now, since the L, you have to compare these two now. This and this. This is the first equation. This is the second equation. Since LHS are same, both are same, so RHS should be same. So equate these two RHS and get the value of sigma C. So sigma C you can find out by equating the RHS. That means two unknowns have been reduced to one unknown. Once you get sigma C, then you can find out sigma S by substituting in one of the equations. So they are the stresses. Once you know the stresses, forces can be found out by multiplying by the respective area. Sigma S into AS is your PS, sigma C into AS is your PC. Okay, you will be getting in newtons. Finally, you convert that into kilonewton. So final check is when you add these two forces, it should be equal to total force. So total force given here is 100. So 57.05, 42.95. If you add that, you will get 100 kilonewton. So that's what you have to do. And if they ask you to find delta LS or delta LC, that is the deformation in the compound bar, they are equal. So what you can do is delta LS, we know that it is PS LS divided by AS ES. So once you know PS, you substitute that. So PS into LS. LS, of course, here it is not known. If they give that, you can find out. Okay. If they give that, you can find out LS. Suppose if it is let us say 100 mm or 200 mm, substitute that divided by AS ES. AS you know, ES value you know. So if they give the length, you can compute the deformation also. That is about one point. Similarly here, this is a concrete column problem. In the case of RCC column, you have concrete and steel. Two materials are there. So because steel is strong in tension, concrete is strong in compression. In the building design, each column, the structural elements of the building, they will be subjected to a lot of tensile, compressive, shear, torsion, all the types of forces. So to take care of compression, concrete is provided. To take care of tension, steel is provided. Shear, of course, both concrete and steel, they are good in taking shear. So that's why that RCC has been developed, that you are going to study in detail in your semester in RCC subject. So here the total column, on the column, the load acting is 600 kN. Size of the column is 230 mm by 400 mm. See here, width is 230, thickness, depth is 400 mm. It is reinforced with 8 bars. He has given 8 bars of 20 mm, 12 mm diameter. Okay, 12 mm diameter has been given. So area of steel you can calculate. So each bar has got 12 mm diameter. So 8 into 5 by 4 into 12 square. That is the area of steel. Area of concrete is total area minus area of steel. Because steel is embedded or imposed within concrete, we have to deduct that area. So area of concrete is this much. So once you know the areas, now use the respect same equilibrium condition. Sigma S AS plus sigma C AC is your P. So sigma S and sigma C, they are the unknowns here. Stress in steel and stress in concrete. Here he has given the modular ratio. One thing is called, what do you mean by modular ratio? Means it's the ratio of Young's modulus of steel to Young's modulus of concrete. ES divided by EC is known as modular ratio. So sometimes they will give that word. Otherwise, they may give the value of ES and EC separately. Or they can give the value of M, modular ratio, M value, which is nothing but ES divided by EC, 18.67. He has given. So we have to use the same two equations, equilibrium equation and strain compatibility equation. Solve that. We are going to get the answer. So next problem also it is same. So all these you can look into that. All these are compound bar problems. So this is what I wanted to explain. So this is also compound bar problem. All this I had explained in our class. Just go through that and principle of superposition states that the effect of the resultant total effect of the forces acting on a member is equal to the sum of the effects due to individual forces taken separately. The effect means it can be anything: stress, strain, deflection, deformation, bending moment, shear force. So those things we are going to study in detail. So they are called as the effects. So that is called as principle of superposition. So when you are when a body is subject to number of forces, so if you add the effect of individual forces, then that should be equal to the effect of the resultant. Resultant is nothing but the sum total of all the forces. You know what about result? What do you mean by resultant? It is a single force which can replace number of forces acting on a body. That is resultant. The effect of a resultant is equal to the sum of the effects of individual forces. That is the meaning of principle of superposition. So that's what. Then modulus of rigidity I explained. So just like modulus of elasticity, you have modulus of rigidity or rigidity modulus or shear modulus. There are three words. Modulus of rigidity, rigidity modulus or shear modulus, denoted by GRC, is the ratio of shear stress to shear strain. So just like linear stress to linear strain is Young's modulus, shear stress divided by shear strain is rigidity modulus. So shear means it is like this. When a force acts tangential to the area, so it distortion. We call it as distortion. It distorts like this, and whatever angle it creates, so this angle will be very small, gamma. That is called as the shear strain. And delta is the linear deformation. Gamma is the angular deformation, or it is called as a shear strain. So since gamma is very small, this gamma can be equated to tan gamma. Tan gamma is delta divided by this h, whatever you can take. So this delta divided by h is called as the shear strain. So the ratio of tau is nothing but F divided by A. So shear force is acting like this. When the shear force is divided by the corresponding area F by A, you are going to get tau. Tau is called as the shear stress as usual, Newton per mm square. Shear strain, it doesn't have any unit. So the ratio of that shear stress to shear strain within elastic limits is known as the modulus of rigidity or shear modulus or rigidity modulus. You have one more called Poisson's ratio, another elastic constant, which is defined as ratio of lateral strain to linear strain. So as I already told, when a bar is subjected to force in one direction, suppose if it is tensile force in one direction, it elongates in that direction, but it contracts in the other two directions. X direction, if it elongates, Y and Z directions, it will contract. So the other two directions, they are called as lateral direction or transverse directions. So if you calculate the strain in the lateral direction divided by strain in the linear direction, that ratio is called as the Poisson's ratio. Okay, so lateral strain divided by linear strain is called as Poisson ratio. All are within elastic limits only. Whenever you are doing, that is why these are called as elastic constants. So this mu value you can take 0.25 to 0.3 for steel, 0.15 for concrete, for rubber it is 0.5. Okay, so this is some of the definitions, elastic constant definition. One more is bulk modulus of elasticity, K. So sometimes stress will act on all the three sides, x, y, on all the three directions, and equal. It is subjected to equal stress. Sigma x is equal to sigma y is equal to sigma z. Then we define what is called as bulk modulus of elasticity. Bulk means volume. So when the stresses act in all the three directions, volume will come into picture. So bulk modulus of elasticity K is defined as the ratio of bulk stress to volumetric strain. So when you talk about bulk modulus, you have to take the volume into picture. So volumetric strain will come in the denominator. So bulk stress divided by volumetric strain. So this is called as bulk modulus. Now all these four, Young's modulus E, rigidity modulus G, bulk modulus K, Poisson's ratio mu, they are all called as elastic constants. Elastic constants. Okay. So this is what I wanted to explain you today. So this generalized Hooke's law, I think you can understand, is the extension of principle of superposition and Hooke's law. Then after this, I think I did expressions for volumetric strain for rectangular rod, rectangular section, then sphere and cylindrical. Then some problems I did using that generalized Hooke's law. Then after that, temperature stresses, I think I covered. Temperature stresses, yes, that is there, I think. Yeah, this. This. Yeah, this one. Diagonal tension, diagonal compression, and temperature stresses. Okay, what is the class tomorrow you have? Yes?
No, sir.
Tomorrow you don't have class?
We have
Yes, sir,
BMT lab we have, sir.
Lab ಇದೆಯಲ್ಲ ನಿಮಗೆ ವಿಡಿಯೋ ನಾದು ವಿಡಿಯೋ
ಹಾ ಸರ್ ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡ್ತಾರೆ ಆಮೇಲೆ ವಿಡಿಯೋ
ಎಷ್ಟೊತ್ತು ಕ್ಲಾಸ್ ಅದು ಹೌ ಮಚ್ ಟೈಮ್ ವಾಟ್ ಇಸ್ ದಿ ಟೈಮಿಂಗ್ಸ್ ಆಫ್ ದಟ್ ಕ್ಲಾಸ್
ಸರ್ 11:45 ಮುಗಿಯುತ್ತೆ ಸರ್ 9:30 ಸ್ಟಾರ್ಟ್ ಆಗಿ
9:30 to 11:45
ಎಸ್ ಸರ್
2 hours ಅಲ್ವಾ
ಎಸ್ ಸರ್
ಹಾಗಾದ್ರೆ ನೀವು ಮತ್ತೆ ನೋಡೋಣ 11:30ಗೆ ಏನಾದ್ರು ಮುಗಿದ್ರೆ ನೀವು ಕನೆಕ್ಟ್ ಆಗಿ, ನಾನು ಇನ್ನೊಂದು ಸ್ವಲ್ಪ ಬೇಕಾದ್ರೆ ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡ್ತೀನಿ 12:30 ತನಕ, ಆಯ್ತಾ?
ಎಸ್ ಸರ್.
ಓಕೆ, ನಿಮ್ಗೆ ಅದು ಟೆಂಪರೇಚರ್ ಸ್ಟ್ರೆಸ್ ಮತ್ತೆ ಜನರಲೈಸ್ಡ್ ಹುಕ್ಸ್ ಲಾ ಅವೆರಡು ಹೇಳಿದ್ರೆ ಆಯ್ತು, ರಿವಿಷನ್ ಆದ ಮೇಲೆ ಓದ್ಕೊಂಡಿರಿ. ಸೊ ನಾಳೆ ಟೈಮ್ ಸಿಕ್ಕರೆ ನಾನು ಹೇಳ್ಕೊಡ್ತೀನಿ, ಆಯ್ತಾ? ಬೇಕಂದ್ರೆ ನಿಮಗೆ ಬೇಕಾ ನಿಮಗದು?
ಪರವಾಗಿಲ್ಲ
ಬೇಕಾ
ಸರ್,
ನಿಮ್ಗೆ ಅದು? ಓದ್ಕೊಳ್ತೀರಾ?
ಹಾ ಸರ್.
ತೊಂದರೆ ಇಲ್ವಾ? ಸರಿ, ಹಾಗಾದ್ರೆ ತೊಂದರೆ ಇಲ್ಲ. ಚಾಯ್ಸ್ ಇರುತ್ತೆ, ನಾನೇನೋ ಹೇಳಿದ್ನಲ್ಲ ಪ್ಯಾಟರ್ನ್. ವಾಟ್ ಇಸ್ ದಿ ಪ್ಯಾಟರ್ನ್? ಐ ಟೋಲ್ಡ್ 5 questions will be given, 10 marks, 5 questions will be given. Among the 5 questions, 3 questions will have choice, 2 questions ಕಂಪಲ್ಸರಿ ಇರುತ್ತೆ. 10 marks ಗೊತ್ತಾಯ್ತಲ್ಲ? 10 marks ನಲ್ಲಿ ಎ ಬಿ ಇರುತ್ತೆ, ಒಂದೇ ಇರುವುದಿಲ್ಲ. ಒಂದು ಥಿಯರಿ, ಒಂದು
ಸರ್
ಪ್ರಾಬ್ಲಮ್.
ಮಲ್ಟಿಪಲ್ ಚಾಯ್ಸ್
ಎಸ್,
ಇಲ್ವಾ? ಮಲ್ಟಿಪಲ್ ಚಾಯ್ಸ್ ಇಲ್ವಾ ಸರ್?
ಮಲ್ಟಿಪಲ್ ಚಾಯ್ಸ್ ಇಲ್ಲ. SOM ನಲ್ಲಿ ಮಲ್ಟಿಪಲ್ ಚಾಯ್ಸ್ ಕೊಡ್ಲಿಕ್ಕೆ ಆಗಲ್ಲ. ಥಿಯರಿ ಸಬ್ಜೆಕ್ಟ್ ಆದ್ರೆ ಕೊಡ್ಬೋದು. ಡೆರಿವೇಶನ್, ಒಂದು ಸ್ಮಾಲ್ ಡೆರಿವೇಶನ್, ಒಂದು ಪ್ರಾಬ್ಲಮ್ ಆ ತರ ಕೊಟ್ಟಿರ್ತೀನಿ, ಆಯ್ತಾ? 4 ಮಾರ್ಕ್ ಡೆರಿವೇಶನ್, 6 ಮಾರ್ಕ್ ಪ್ರಾಬ್ಲಮ್, ಆ ತರ ಇರುತ್ತೆ, ಗೊತ್ತಾಯ್ತಲ್ಲ? ಫಾಸ್ಟ್ ಆಗಿ ಮಾಡ್ಬೇಕು. ಎಕ್ಸಾಮ್ ನಲ್ಲಿ ನಿಮ್ಗೆ 3 ಕ್ವಶನ್ ಇರುತ್ತೆ. ಕ್ವಶನ್ ಪೇಪರ್ ನೋಡಿ ನೀವು, ಗೊತ್ತಾಗುತ್ತೆ. 20 marks ನಲ್ಲಿ 3 ಕ್ವಶನ್ ಇರುತ್ತೆ ಅಲ್ವಾ? ವಿಲ್ ಬಿ ಹ್ಯಾವಿಂಗ್ 3 questions, ABC ಇರುತ್ತೆ. ಸೊ ತುಂಬಾ ಫಾಸ್ಟ್ ಆಗಿ ಮಾಡ್ಬೇಕು. ಸೊ ಒಂದ್ರಲ್ಲಿ 3 ಕ್ವಶನ್ ಅಂದ್ರೆ ಯು ಹ್ಯಾವ್ ಟು ಆನ್ಸರ್ 5 questions. 5 modules ಅಲ್ಲಿ ಔಟ್ ಆಫ್ 10 questions ಯು ಹ್ಯಾವ್ ಟು ಆನ್ಸರ್ 5 questions. 15 questions ಆನ್ಸರ್ ಮಾಡ್ಬೇಕು ನೀವು 3 hours ಅಲ್ಲಿ. ನಿಮ್ಗೆ ನಾಳೆ ಸಿಗೋದು ಎಷ್ಟು ಟೈಮ್? 1.5 hours ಅಲ್ವಾ? 1.5 hours ಸಿಗುತ್ತೆ ನಿಮ್ಗೆ ಅಷ್ಟೇ. ಸೊ 1.5 hours ಅಲ್ಲಿ ನೀವು 10 ಕ್ವಶನ್ ಮಾಡೋಂಗ್ ಆಗ್ಬೇಕು. ಅಂದ್ರೆ ಒಂದು ಸಣ್ಣದು ಇರ್ತದೆ, ಒಂದು ಸಣ್ಣದು ಒಂದು ಪ್ರಾಬ್ಲಮ್, ಹಾಗೆ ಥಿಯರಿ ಒಂದು ಕೊಟ್ರೆ ಪ್ರಾಬ್ಲಮ್ ಒಂದು ಕೊಟ್ಟಿರ್ತೀನಿ, ಹಾಗೆ ಗೊತ್ತಾಯ್ತಲ್ಲ? ಸೊ ಮತ್ತೆ ಫಸ್ಟ್ ಮಾಡ್ಯೂಲ್ ಅಲ್ಲಿ 4 questions ಕೊಡ್ತೀನಿ, ಸೆಕೆಂಡ್ ಮಾಡ್ಯೂಲ್ ಅಲ್ಲಿ 1 question ಕೊಡ್ತೀನಿ. ಕಾಂಪೌಂಡ್ ಅಲ್ಲಿ 1 question, ಒಂದಂದ್ರೆ ಅದು ಐ ಮೇ ಗಿವ್ ಚಾಯ್ಸ್, ಗೊತ್ತಾಯ್ತಲ್ಲ? ಎರಡು ಕೊಟ್ಟು ಒಂದು ಮಾಡಿ ಅಂತ. ಫಸ್ಟ್ ಅದರಲ್ಲಿ 4 question, 40 ಮಾರ್ಕ್ ಫಸ್ಟ್ ಮಾಡ್ಯೂಲ್, 10 marks ಸೆಕೆಂಡ್ ಮಾಡ್ಯೂಲ್, ಆಯ್ತಾ? ಓಕೆ, ಡೌಟ್ ಏನಾದ್ರು ಇದ್ರೆ ಕೇಳಿ, ಆಯ್ತಾ? ಯಾವ್ದು ಇದ್ರೆ ಕೇಳಿ ನೀವು, ಅದರ್ವೈಸ್ ಸ್ಟಡಿ ವೆಲ್. ನೀವು ಈಗ ನಾ ಏನ್ ಮಾಡ್ತೀನಿ ಕ್ಲಾಸಲ್ಲಿ, ಏನ್ ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡಿ ಎಲ್ಲ ನೋಡ್ಕೊಳ್ಳಿ. ಮತ್ತೆ ಪ್ರಾಬ್ಲಮ್ಸ್ ಅಸೈನ್ಮೆಂಟ್ ಎಲ್ಲ ಮಾಡಿ ಇಟ್ಕೊಂಡಿರಿ. ಸಬ್ಮಿಷನ್ ನೀವು ಬೇಕಾದ್ರೆ ಫ್ರೈಡೆ ಮಾಡಿ, ಬಟ್ ಅಟೆಂಪ್ಟ್ ಮಾಡಿ, ಎಲ್ಲ ಪ್ರಾಬ್ಲಮ್ಸ್ ಸೊಲ್ಯೂಷನ್ ಮಾಡಿ ಇಟ್ಕೊಳ್ಳಿ, ಬಿಕಾಸ್ ಟೆಸ್ಟ್ ಯೂಸ್ ಆಗುತ್ತೆ. ಓಕೆ,
ಹಾ ಸರ್.
Yes, sir.
ಓಕೆ, ಐ ವಿಲ್ ಕ್ಲೋಸ್ ದಟ್.
ಥ್ಯಾಂಕ್ ಯು ಸರ್.
ಐ ವಿಲ್ ಟೇಕ್ ದಿ
ಸರ್
ಅಟೆಂಡೆನ್ಸ್.
ಅಟೆಂಡೆನ್ಸ್
ಏನಮ್ಮ? ಅಟೆಂಡೆನ್ಸ್ ತಗೊಳ್ತೀನಿ. 15 ಸ್ಟೂಡೆಂಟ್ಸ್ ಇದ್ದಾರೆ. 1828.
Present, sir.
1830.
Yes, sir.
19002.
Yes, sir.
3.
Yes, sir.
5.
Present, sir.
6. Deviation.
Present, sir.
7.
Present, sir.
10.
ಪ್ರೆಸೆಂಟ್ ಸರ್.
12. 11.
ಪ್ರೆಸೆಂಟ್ ಸರ್.
12.
ಪ್ರೆಸೆಂಟ್.
Present, sir.
Then 13.
Present, sir.
17.
Present, sir.
18.
Present, sir.
19.
Present, sir.
21.
Yes, sir.
Okay. Okay.
Sir,
Good luck.
16 present ಇದ್ರು sir.
16 present.
ಇದ್ರು
ಹಾ
ಸರ್.
ಸರ್, ಇವಾಗ ತಾನೇ ಲಾಗೌಟ್ ಅದು.
ಲಾಗೌಟ್ ಆಗ್ಬಿಟ್ರ ಅವರು?
ನೆಟ್
ನೆಟ್ವರ್ಕ್
ಪ್ರಾಬ್ಲಮ್.
ಮೆಸೇಜ್.
ನೆಟ್ಗಿಲ್ಲ ಅಂತ. ಸರಿ, ಓಕೆ, ಚೆನ್ನಾಗಿ ಓದ್ಕೊಳ್ಳಿ.
ಥ್ಯಾಂಕ್ ಯು ಸರ್.
ಓಕೆ, ಥ್ಯಾಂಕ್ ಯು.
ಥ್ಯಾಂಕ್ ಯು.